This is a crash course in soil science to help get you ready for the AP exam. Soils looks like it's only a little part of maybe unit 4 and 5, but it unpacks into a lot of the other units throughout the entire course. But this is going to be the basics on some things with soil science, soil formation, and soil conservation, as well as negative impacts of overuse of our soil resources. First thing to know is potting soil is not actually soil. It's almost all organic matter, usually with some things like perlite and vermiculite added. When we're talking about soil, it's not the stuff you put your houseplants in. This is the stuff that comes from the ground. It varies in colors depending on where you are in the world. But within any given school area, you usually all will have pretty consistent soils in your surrounding community within a few miles, unless it's been altered by humans. Naturally, soil takes a long time to form. On the average, it's 500 years to make an inch of soil, but that's on the average globally. Where I grew up in northern Wisconsin, it takes about 10,000 years to make an inch of soil. The reason we know that in northern Wisconsin is there's only an inch and a half of topsoil, and the last ice age scraped away all of our soil. So, since the last ice age, gaining an inch and a half of topsoil means about 10,000 years to make an inch of soil up there. The APES exam probably will not ask you how long it takes to form soil. These are the main things that interact. Like soil parent material would be things like sand, silt, and clay. It's the rock stuff. Climate, obviously relating to both temperature and precipitation. Topography, or the slope of the hillside, can further affect soil formation, as do plants and animals, and time. The other thing is soil doesn't actually form in all places in the world. Some places are so dry that we don't have soil formation, like in certain deserts. So when we're talking about soil formation, it's, in ideal circumstances, you could have soil form. And a good thing to know is sometimes in the APES exam, they will ask you if something is primary or secondary succession. Um, Primary succession is when you actually see what we call soil forming factors. So if there's life coming to a lifeless area, so something like, things colonizing a new lava field would be primary succession. So when in doubt, if you're not sure if it's primary or secondary succession, ask yourself if you're seeing the formation of soil in the case they're describing. If not, it's usually going to be secondary succession. These are all the things that, like, where soil becomes a lot more interesting. Maybe not so much in soil formation. Right now, a lot of you are hearing this podcast, watching it, thinking, what the hell? This is going to be so damn boring. Soils get a lot more interesting as you start looking at how humans have interacted with them. By the way, for the APES exam, these are just some of the various places where soils come up. Often when you study for this exam, you might think it's only a little bit of Unit 5, but soils interact with all of these other layers. One way to talk about this is something as simple as the Dust Bowl. The Dust Bowl was one of the greatest moments of soil erosion, or worst moments of soil erosion in world history. And when you look at textbooks, they don't do it justice. Textbooks usually show you things like, this is how much of the area, Earth, or the US was impacted by Dust Bowl. The red was the really bad areas, and then everybody else was slightly affected. In fact, at the peak of the Dust Bowl, the dust was blowing all the way in this circle. Places like New York City, actually, and Washington, D.C., had the sunlight blocked out by dust storms coming in from Oklahoma. In parts of the East Coast, they could actually figure out where the dust storm was originating based on the color of the soil that was landing on the streets. So this was a catastrophic, huge impact. We'll talk more about this in a bit. First thing to know, soil is officially a mixture of all of these things. It's going to be parent material, living organisms, organic material, decomposing stuff that's no longer alive, water, and air. The ratios vary depending on what kind of soil you're talking about. And yes, a lot of you will others by saying, calling it dirt just to annoy teachers and soil nerds like myself. The difference between soil and dirt is not alive. It does not have living organisms. The term we often say in soil science is dirt is dead. One of the coolest things about soil is the part where there's nothing there, called interstitial spaces. If you look closely at soil under a microscope, it almost looks like bricks or rocks in a fieldstone wall, but there's these empty spaces between it. Good soil tends to be a little fluffy. Those empty spaces are really important because those are required for water storage, water percolation, and root development, as well as air getting to the roots of plants. Most plants breathe through their roots. If there's no interstitial spaces, the plants can suffocate. The volume of those empty spaces is called porosity. The permeability, it's hard to describe permeability without reusing the word permeability. The fancy way of describing permeability is it's how well water would drain through stuff or air goes through soils. Or officially, it is the connectivity of the interstitial spaces. When we look at the ratio of sand, silt, and clay in soils, it tells us a little bit about porosity and permeability. Those circles on the bottom represent sand as the largest, silt by scale, and the little dot would be clay. They're all just different sizes of rock. If you take a rock and pulverize it smaller, you get gravel. If you pulverize the gravel, you get pebbles. From pebbles, you would get sand, and then from sand, you get silt, and then from silt, pulverize more, you get clay. And this is an important thing to know. The exam will often ask you about this. Clay has some weird things. And a lot of the textbooks and labs you might be doing are telling you that clay has high porosity and high permeability. We'll get into clay in a second, but basically, sand has the highest porosity and highest permeability. Silt is medium for both. Clay generally has little to no porosity or permeability, but clay is a weirdo freak. I'm a potter as well. I love working with clay, but it is not a normal substance. Some things to be on the lookout for in your textbooks and on review videos I've seen, as well as even in some of the labs. Soils in some areas, the sand, silt, and clay that make up a soil might be different colors, but it's not guaranteed. Where I grew up in Wisconsin, the sand, silt, and clay were all the same color. So soil particles are not color coded is an important thing to know. Most textbooks get everything really wrong about clay. And also, loam is not a particle size. So that picture there came from a review website, and whoever wrote that is a big dummy head because clay is one type of soil particle, sand is a different size, silt is a different size. Loam is not one single soil particle. I've even seen lab kits getting sent to AP Enviro teachers, including samples of loam for a soil particle, but it's actually not a single soil particle size. But now here's the cool thing about clay. If you've ever worked with clay in an art room, we're not talking about like Play-Doh or the brightly colored synthetic clays you get at the grocery store. We're talking about the clay that you would use and then fire to make ceramics. That is actually mined from the earth, and it is the coolest stuff because clay, when it gets wet, forms a gel. It's called a Newtonian fluid. Clay is actually amorphous. It's plastic, meaning you can mold it, and it's even a little bit elastic, where sometimes it will bounce back to its original shape. And it swells when it gets wet, but it doesn't actually have empty space. So if you get clay wet and you slice it open and look at the particles, you would not see empty interstitial spaces. It forms a gel. That's why potters can shape it to make ceramics, and then you can fire it in the kiln. Now, the weird thing is the misconceptions about clay are because of one stupid thing. When clay dries, it shrinks. And that shrinking is called cementing. So here's a clay pan soil, as it's called, which is dried out, and you see all those cracks. When the clay dries out and gets all those cracks, all of a sudden it has high porosity and high permeability. Now, the weird thing is if that clay gets wet, it will now disintegrate. If you've ever worked with art or clay in the ceramics class or a pottery class, if the clay that you're working with gets completely dry and you get it wet, it just turns into like a foamy mess and disintegrates. But the process of clay shrinking when it gets dry is called cementing. This becomes an issue with a lot of things in environmental science, is this one little freaky thing that clay does. Also, clay causes other things. So if you've been watched the news, Burning Man had heavy rains, and that dried out lake bed actually was clay. So when it got wet, it became a fluffy, shapeless mess and trapped cars. And then when they abandoned the cars, they literally got stuck back in the clay. Now, the reason why there's all the misunderstandings about clay is about 8 years ago, all of the companies that teachers use to get supplies to teach about soils, they started sending clay in a powdered form, which is not found in nature. Clay in a powdered form is used in ceramic studios. It's machined, it's ground up. It is not found in nature because when clay dries out in nature, it forms these clods or peds, these big chunks of clay. It would not be found looking like this. So the problem is when that clay comes in a powdered form, if you try to add water to it to figure out what we call its porosity, which you probably have done a lab with that, because it fluffs up and forms this gel, you get a reading that it has high porosity, but you're not actually measuring the porosity of that clay. You're measuring the weird attribute of clay powder that it just sucks up water. Clay is weird in that way. Like if you have a high clay soil and plants are growing in there, if there's not enough water, the soil will start through osmotic pressure pulling the water out of the plants, killing them faster. And going with that, the way you officially measure porosity is volume by displacement. So this right there is actually a lab setup where someone's working with clay powder, and it's going to give them a false reading on the clay porosity. It does work really well with things like sand and gravel, and that's a better way to do it. And by the way, the method of measuring volume by displacement was developed by Archimedes. Permeability, you'll be doing some permeability things probably with your teachers. Usually it's putting the soil in the funnel, watching the water go through. It's the official way we do this in soil science is they dig a hole and they pour a measured volume of water in there and they time to see how long the water goes through. Now going back to those soil particles right here, often you're thinking which one's the best. Now as human beings, you're all thinking, I bet it's the middle one. I bet it's silt because it's like baby bear's porridge. It's not too hot, not too cold. The actual best soil is a mixture of all three. This weird pyramid, which you will see on the AP exam, and your teacher will have you tinker with this as well, is called the soil pyramid. And each axis refers to the percentage of sand, salt, and clay. And your teacher will do a lab where you figure out how to separate sand, salt, and clay. It's actually really simple. Sand is the biggest, so it settles in a watery solution in about 30 seconds. Silt takes 30 minutes. Clay will be settled if you have any by the next day. The ideal soil that we want, like the best soil, if for myself as a gardener and in the US for agriculture, is loam. Loam is just this happy mix of sand, salt, and clay. That's why it's not its own individual particle. It's like the Chex Mix of awesomeness of soil. Now, the way you use the pyramid is tricky. Your teacher will set one up for you, or you'll be doing this a lot in your classes probably. I made a color code line showing how to do it. One of the tricks for using this is in the case of each soil percentage. If we know we have 45% sand, you have to find the percent sand on the bottom. And then the trick is the longest line is 0. So then it's 10, 20, 30, and then you get 45% sand. You snap a line down. You can do this more easily on paper if you have a ruler. You'll see the 35% silt. The arrow's a little off. Sorry about that. And then the 20% clay. So something like that would be loam. And that's how we use the soil pyramid for things like forestry and agriculture, because it tells us based on these soil things, these are the best trees to grow in this, forest, or if we're managing a forest, or these are the crops that will grow best in these soils. One thing that we did until the 60s or 70s is people thought we could use this to fix soils. Like if we had clay, like where I live now, my soil is almost entirely clay. Like we can add sand and we can break up the clay. If you add sand to clay, you've just made adobe. It's not going to actually improve the soil. So remember, the soil pyramid is diagnostic, meaning it describes it. It does not tell us how to improve it, because generally the soil you have will be the soil you have. We do use the soil pyramid to do lots of things, including how to design, like besides agriculture, we can use it to determine what kind of footings, what kind of foundation a structure will need if you're building a house or an apartment or anything. It also tells us a lot about flood control. If we have to plan for water in heavy rainfall areas, if you have clay soils, you have to allow for more drainage in your area because the clay soils often don't absorb the water that fast. Even for rural areas, this tells us a lot about how we make our septic tanks. Just remember, you can't use it. By the way, the way you fix any soil, whether you have clay, sand, or silt, or loam, is you add compost. Organic material is what consistently fixes any soil. These are the five main vocabulary words you'll hear about in soils as well. So the soil vocabulary, we're going to start with erosion. It's soil getting carried away. Usually it's moving downhill, but wind can carry it any direction. And it's usually moved either by gravity, water, or wind, or a combination of the three. So the picture on the top right is mud in the mouth of the Amazon River where it meets the ocean. That would be an example of erosion. Not all erosion is bad. Some erosion is natural. In this case, those nutrients in that soil help start a food chain in the mouth of the Amazon River. Picture on the bottom left, that is a mudslide where I live here in Costa Rica that happened about a year ago during heavy rains. And that was caused by a mixture of gravity and heavy rainfalls. Picture on the bottom right is erosion caused by wind. So those are each examples of that, and that is in part of the Dust Bowl, which we'll talk about in more detail. Here's some crazy erosion. This is soil dust from the Amazon or from the Sahara Desert getting carried by our trade winds over the Atlantic Ocean. That dust heats up in the sun and forms low pressure. So indirectly, erosion is one of the things that leads to the formation of hurricanes in the Atlantic Ocean, because the more dust we have in the Sahara Desert blowing into the Atlantic Ocean, the more we develop these tropical lows that can grow into hurricanes. Also, glaciers cause erosion. So where I grew up in northern Wisconsin, glaciers in the last ice age took away all of our topsoil and dropped it off in southern Wisconsin and what became Illinois. For those of you out on the East Coast, the Long Island is part of a terminal moraine that connects all the way to Nantucket and Cape Cod and Martha's Vineyard. And that is the tail end of the last ice age, how far the glaciers reached. So below that line, you will have more soil than north of those lines as a result of the glaciers. So erosion is not always ideal. Usually it's problematic, especially when humans are involved. Ways you can reduce erosion are as simple as increasing tree cover. The reason why trees are great, roots are strong, they're flexible, they hold the ground, but they also provide avenues for the water to soak into the ground rather than running across. Terracing is used in a lot of the world, especially in agricultural areas, to reduce erosion like you see in this picture. Contour plowing, I'll show you in that in a few slides. Also, ground cover left, especially in the US over the winter, cuts down on wind-related erosion in the winter. And then I'll show you gaveones at the tail end. So here's contour plowing, and it's plowing following not straight lines, but the contour lines, and that can reduce water erosion. Leaving cover on fields is another way. So this is called no-till agriculture, or green manures, where you plant things like clover on your fields in the winter The clover holds down the soil, but it also puts some more nutrients like nitrates back into your soil. Here are gaviones, which is used a lot in Central and South America. These things are amazing. They're about 6 feet high, each row. So that would be an 18-foot high wall. And they're made with metal cages and rocks. The rocks have to be stacked in a careful way, and it allows water to drain through so that you don't get waterlogged soils that are more likely to have mudslides, but they have a lot of strength to help hold up hillsides. Weathering is not the same thing as erosion, and be on the lookout for this. On the APES exam, students often write weathering and erosion interchangeably, and they're not interchangeable. Erosion is soil moving. Weathering is big rocks breaking down into small rocks, and it can be caused by anything, changes in temperature, wind, water, particles. And there's obviously a big example of weathering. So weathering is big rocks becoming small rocks, or sand grinding down eventually to become clay. Compaction is when we put too much weight on the soil, and compaction can be caused by things like plowing fields too much, foot traffic. If you go to city parks, or if there's an area where people shortcut across the grass, like in this picture, all of those footsteps pretty quickly can cause compaction of the soil, and you'll see it here. The grass is dead. The reason why is not just because the footsteps themselves killed the grass, but now the grass can't get established because the ground got packed so tight that roots can no longer grow to establish new grass. So it's reduction of porosity and permeability. And you see a picture, and it's just basically you press the soil down too much. The easiest way to repair compaction is get the ground to freeze solid in the winter and cold climates, or you might see this in school fields or grassy lawns. It's called an aerator, where it's this big metal drum that pulls out little plugs of the soil and leaves it on the surface. That gives some area for air to re-enter the soil, and then after a few rainstorms, that helps fluff your soil back up. Desertification is the loss of fertility of the soil. Here's an example of desertification. Here's an example of desertification in, I believe this is the Amazon. No, it's not the Amazon. Those are pine trees. Don't know where this is, but you can see heavy logging. They removed all the trees, and now you're just seeing really unhealthy looking soil. So this can be caused by unsustainable agriculture or clearing out forests and not replanting them. In your history class, you heard about the Fertile Crescent in Mesopotamia being the origin of civilization in Eurasia. If you go to those areas called the Fertile Crescent now, years of agriculture, thousands of years of agriculture have destroyed the soils. So desertification is a big risk. It's not quite the same thing. It's not the same thing as erosion, but it is losing the nutrient capacity and the fertility of your soils. A lot of agricultural land throughout the world shows a mixture of all of those things, as well as one other thing I'm going to show you called salinization. Here, yes, is a soil scientist, not me. On the left side of the photo, those are traditional tall grass prairie root structures. On the right side is modern agriculture grown in the same soil, and you can see the roots don't go down nearly as deep. That can lead to lots of things, including compaction and erosion and desertification. In the Corn Belt, which is areas where we grow corn, like Nebraska and Iowa, we're losing about 1 inch of topsoil every year currently with our current agricultural methods. Salinization is buildup of salts, usually calcium salts or magnesium salts, when we use groundwater to irrigate or water things. And you can see this, like if you have any, sad looking potted plants in the corner of a classroom or in your house, look to see if you see some white powdery stuff on top of the soil, because what that actually is salinization. The way to treat that with houseplants is you just take them outside and give them rainwater, and that will eventually wash through. In a lot of the world where we have salinization from overusing groundwater to irrigate crops, those salts can actually impair plant development. The easiest way to resolve that is to try to use more natural rainfall and try to find plants that need less irrigation for crops. So there are the solutions. And basically, if you stop irrigating with groundwater, those salts will go away on their own. The other way you can get salinization, which happens in coastal areas sometimes, is if too many people are drawing out groundwater, it can start pulling salt water from the ocean into the aquifers underneath your community. With soils, we also have soil horizons. And these you usually will not find near your school. These take thousands of years to get established. And not all biomes have all of these. The reason why you won't see these at your school is any place where you have an urban or suburban environment with home construction and schools, there were a lot of bulldozers that moved the soil around. So it's all been mixed up. So you won't see these. To find soil horizons, you'd have to go to some undisturbed forest or prairie or other ecosystem that's not been plowed or had excavators move the soil. The AP exam does want you to be familiar with these. So we're going to go through them. The nice thing is there's O stands for the organic layer on the top, and the rest are in alphabetical order. Big thing to know is not all biomes have owl horizons. The O horizon is the organic layer. In forestry, we actually call this Duff, like the beer from The Simpsons. People often remove the O horizon for aesthetic reasons or to reduce fire danger. So where I live here in Costa Rica, a lot of my neighbors are convinced because of legends that if they don't remove the leaves from their yards, they will get more snakes in their yards. Because we have a lot of venomous snakes here, like the Terciopelo. The weird thing is it doesn't actually determine whether or not you have snakes to remove the leaves. The people that remove the leaves, though, often get stung or bit by the snakes. Since so it turns out in Spanish, they say you get stung by a venomous animal, you don't get bit by it. But so the thing is, when you remove those leaves contain the nutrients that help the forest and plants regrow. Now, in a lot of the forested parts of the world, drier forests, like in the US, when there's a wildfire, they'll often remove the organic layer at the edge to try to contain the fire because often the wildfires crawl through the organic layer. So it's not always good to remove the O horizon. Sometimes we do it, though, for wildfire issues. Now, removing the O horizon does increase your risk of erosion, decreases nutrient loads, as well as the formation of humus, which is the organic, mulchy part of your soil. On the APES exam, they almost always ask about the A horizon. They rarely ask about the B horizon and C horizon. And this is going to be the mixture of sand, salt, and clay, but also a huge amount of organic material and living organisms. And this is what creates what we call arable land, which is the land good enough for growing food. It's what we need for agriculture. So, and the A horizon can vary in thickness, but it's usually dark. B horizon is called subsoil. There's no organic content. They don't really ask about it in the AP exam. This is usually where septic fields go if you have drainage fields go if you have a septic tank. The C horizon is often called parent material or bedrock. Just I'm seeing some textbooks and review pages are now listing the parent material and bedrock as separate horizons. Don't worry about it. They're not going to ask you that on the APES exam. If they do, you can write me hate emails. This is usually where foundations need to be anchored for structures. On the APES exam, they're usually only going to be asking about the A horizon. Now, the E horizon shows up in some textbooks. Where I grew up in northern Wisconsin, we had an E horizon in our forests. It's pretty rare to see an E horizon. It stands for this thing called alluviation, and its water just becomes acidic when it goes through things like pine needles or oak leaves because it picks up these things called tannic acids, and then that acid causes a whitening of the bottom of the A horizon, between the A horizon and the B horizon. So you get this white chalky layer between the two. You're probably not going to see it unless you go to a forest that hasn't been disturbed. But if you ever do see a white chalky layer, people often see it and they think it's like volcanic ash or from an asteroid impact. You're usually looking at an E horizon. Now, here's a good question for you, going back to it. Which of these biomes has the best topsoil? When we talk about topsoils, we're usually looking at what is the content of organic material, also what is the mixture of sand, silt, and clay, and also how thick is the topsoil layer. So we're going to go through these one at a time. So here's a diagram. This comes from a different textbook. This diagram is actually fairly accurate. And overall, like, I'm pretty happy with it, except it does have the A horizon a little bit off on a few. So the crazy thing about this is the A horizon for the deciduous forest is right. The coniferous forest is completely wrong. And honestly, the other ones are not even truly to scale. So let's just go through the crash course. For this exam, they're not going to ask you to know about all soils for all over the world, but it is good to know about these 6 biomes and what their soils look like. So you're going to get a crash course in them. And by the way, that little red dot is where I grew up in northern Wisconsin. And we'll get to that in a second. Which I'll tell you right now, where that little red dot, my hometown used to be called Farmington when they cut down the forest and named the town because it was going to be dedicated to agriculture. All the farms failed because the topsoil was only 1.5 inches thick. It was not arable land. It was not good enough for growing food. So like Massachusetts, you're mostly originally would have been deciduous forest, and you would find about 8 to 12 inches of topsoil. You'll have thick, natural, what we call leaf litter. It's good for agriculture. It's good for growing stuff. That's why there's a lot of, dairy production and cranberries. Tallgrass prairies are the rock stars of the soil biomes. Because tallgrass prairies are not, notice that that's in feet. So if you're, often when I teach about soils to different schools, I've had students in places like Iowa comment that they can't see the soil horizons, and because they've tried and they don't see them. And the reason they don't see them is they'd have to dig down in Iowa about 17 to 20 feet to see the subsoil. It's all topsoil. In the case of tallgrass prairie, most of the energy in that ecosystem is not in the plants, but it's in the roots and in the soil and in the soil microbes. These are the best soils for agriculture. They're just incredible. One reason why the U.S. has a fairly stable economy, even though it doesn't feel like it sometimes, is because we have so much arable land for food production. Shortgrass prairies, they usually don't ask about this on the AP exam. This is used for grazing lands. Tallgrass prairie is pretty cool. Shortgrass prairies, obviously the grasses are shorter, not as much soil. They're usually a little bit drier. They're really only used for grazing land. They're not good for agriculture. Tundra is on the APES exam. It's permanently frozen ground, so it's called permafrost. There's no trees. It does look kind of cool in the warmer months because you see tons of flowers like in this picture. Currently, one thing happening to our tundra is as it's all thawing, it's starting to release methane because there's methane trapped in the frozen stuff. What's there is technically not soil, it's frozen, solid, undecomposed stuff or decomposing stuff. As the tundra thaws, it would give way to the taiga as trees start growing. The only thing you have to know about tundra soils is that they're permanently frozen and they contain methane. Deserts are rock hard soils, and not just because they contain rock, but all the soil, sand, and clay, it gets cemented together by salt crystals because of high rates of evaporation. It's usually highly compacted naturally. If you ever try to dig in the desert, my brother lives in Arizona. He had to rent a jackhammer to put in a new garden because that was the only way to dig in the soil. Weird thing about desert soils is it can be so dry that the water becomes the ground becomes hydrophobic, meaning it repels water. That's why you often have flash floods in the deserts. There's really not much topsoil in a desert soil. Now, tropical rainforests, like where I live, have no topsoil. Absolutely not. The trees are growing right on the subsoil on the B horizon. There is no A horizon. Because the reason why is there's so much rainfall, so much plant growth, and such warm temperatures and rapid decomposition that everything that should be going into the topsoil either goes directly into the trees and the energy enters the canopy of the forest, or it gets washed down into the oceans and rivers. So tallgrass prairies are kind of like an upside down tropical rainforest, because tallgrass prairies, the energy is in the soil. The tropical rainforest, the energy is in fact in the canopy. And the soils are so poor in tropical rainforest that's why you see, like in this picture on the top, those people are sitting on the roots of a tree called a ceiba, which is like, it's nicknamed is the grandfather tree of the forest here. The reason why those roots have that adaptation is the soil is so lousy that there's really not much for the plant to grip to. So it has these roots called buttressing roots to help keep it from tipping over with the heavy rainfalls. Now, urban soils tend to mimic deserts. They're heavily compacted, like you see in this picture. They tend to have salt accumulation from, especially in areas where they put salt on ice. And I'm not anti putting salt on ice in cold climates, because falling on the ice is painful and dangerous. But the soils here have very little porosity and permeability. And usually in urban soils, you won't see horizons. Now, going back to those pictures you saw, the black and white pictures of the soil dust storms, that happened in the Dust Bowl from like the 1920s to the 30s in the US. We'd never had that happen before in the US because there was never technology to cut open the prairie till we developed steel plows. In the 19th century, people used cast iron plows, and the iron would snap trying to cut through the roots of the tallgrass prairie. But once we had steel plows and large powered tractors, they started plowing up the prairie in the 1900s and 1910s and 1920s. The first 10, 15 years went really well, but then they went through a seasonal drought. And here was the change that happened in US society and human civilizations right before the Dust Bowl. And it's called the Green Revolution. The Green Revolution was the process of using fertilizers and pesticides. And with those, don't use those interchangeably. So either mention on the exam fertilizers or mention pesticides, because they have different purposes and they have different environmental impacts. So just refer to one or the other on the exam. So this was the change. Before the Green Revolution, we had small family farms, we had crop rotation, we had use of livestock for grazing and manure, we had multiple different crops and livestock on any given farm. Most of the agriculture at the time was in the eastern states and the Midwest. As we started plowing up the prairie in places like Oklahoma and Nebraska and other places, and Texas, the farms became bigger. We started using large machinery. We automated stuff, so there was less labor required, but we were using more fertilizers and pesticides. But all of those things, one other thing that happened is as these farms got bigger, we stopped doing crop rotation. We stopped, using natural manure. And we plowed up the entire prairie. And it started happening in the late 19 teens, so like early 1920s. There were a few droughts and some crops failed. And according to people that witnessed it, like that started as like seeing small little dust storms, but they kept growing. And the trigger was the black dirt would heat up in the sun and start forming convection and make storms. And those are what you see in these pictures. Now, this is, it's a black and white picture, but if you look, it's darker than night underneath that dust storm. If you got trapped in here, you would not be able to see and you could suffocate from the soil in the air. The Dust Bowl became a feedback loop because as the Dust Bowls grew, all the crops died as the dust storms went through, and they found out later all those soil particles rubbing in the air generated static electricity that electrocuted the plants. It tased them to death. As those plants died, they had more soil that was no longer held down, and the dust storms became bigger and bigger. People tried to replant crops to hold the soil, but they could not get crops to get established because of both the drought and the static electricity was frying the plants. The human impacts for this were awful. Families starved, lots of families lost everything. If you got caught in the storm, you could suffocate. There were cases where people were trying to find their way home, and if they touched a metal fence, like a barbed wire fence, during the storm, they would get electrocuted from the static electricity in the air. Soil would get into your lungs, even inside, causing pneumonia, which could be life-threatening. Families lost everything. A lot of them ended up abandoning their farms, or the banks took their farms, and they fled to California. The Dust Bowl was fixed with the help of FDR, President Roosevelt, Franklin Delano Roosevelt, and part of the New Deal stuff. They won't ask you like who was responsible for that, but what happened was we created the Soil Conservation, or they passed the Soil Conservation Act, created a Soil Conservation Service. Some of the first things they did is they replanted rows of trees called windrows between fields to cut down on the wind erosion. They began researching what else could be done to reduce soil erosion. They created irrigation projects to keep crops from drying out in hot seasons. Not everything with the Soil Conservation Act and FDR was good. One thing that they also created was the Tennessee Valley Improvement Project, which was dedicated to providing irrigation sources throughout the southwestern United States. One of the things that the TVA did is it led to a huge increase in dams, which led to more water loss. And ultimately, that is why there is the Colorado River no longer flows to Mexico, is from all of the dams and diversion projects that were results of the Tennessee Valley Improvement Project. So the reason why we care about soil is because it is the limiting factor for how many humans the Earth can support. And to put it in scale, if one of those apples was the size of the Earth, the sticker would be the amount of arable land we have by volume, including the thickness of the sticker, to grow all of the food we need to maintain human civilizations. And that sticker is getting smaller every year through desertification and erosion. So there's a map with the arable land of the world. And as you can see, the US has a pretty high concentration of it. These are the 4 numbers you will hear for how many people the Earth can support. And as you know, currently we are over 2 of those numbers. The Earth's population, I think, is 8 billion right now. So each of those numbers is actually correct. What varies is what you're eating or how you're living. If everybody ate a US diet, which is higher in protein, the Earth can support about 3 billion people. When I say higher in protein, I'm saying like more animal protein. If everybody ate a diet similar to how people do along the coast of the Mediterranean, where your daily serving of animal protein is about the size of your cell phone, the Earth can support about 7 billion people. If you eat a nearly vegetarian diet, like parts of India, the Earth can support about 12 billion people. And by the way, I'm not telling you to go vegetarian. Going vegetarian is kind of difficult because there's some amino acids that are hard to get. The traditional vegetarian diet that you see in rural parts of India, turns out they were getting some of these trace amino acids from eating insects that were in the grain. 25 billion is a crazy number. That is what a lot of people say for why the Earth can support more people. And they're like, it's a fact the Earth can support 25 billion people. And yes, it can support 25 billion people, but it's based on what's called basal metabolic rate, which is the calories you need to just not die. And when I say just not die, you'd have to be in a medicated coma, like in the Matrix, for the Earth to support 25 billion people. And by the way, like I'm going to have steak tonight. So please understand, I'm not telling you to go vegetarian, but it is, when we talk about human population growth, part of our concern is how much soil we have and what kind of lifestyle do we all want and what kind of food do we want to eat. And also with soils, and soils are important for agriculture. And even if people don't think agriculture is important, before civilization started growing food, they had no evidence of language or traditions or culture. It seems growing our own food, the transition from nomadic to actually staying there and growing our own food and livestock and crops, as soon as we see evidence in every continent where people start growing their own food, that's when we start seeing language, we see writing, we have music, we have art, we have sports, and that's all dependent on agriculture and soils. And by the way, just fertilizers, which are one of the things we use in modern agriculture, are nitrates, phosphates, and potassium. They were invented. The guy who came up with the idea was a German scientist in the 19th century. His name was Justus von Liebig. There's a picture of him looking kind of scary. He came up with this, like, we can make nitrogen, phosphorus, and potassium, nitrates, phosphates, and potassium, and add it to increase plant growth. No one did anything with his discovery because it was too damn expensive. We didn't start using fertilizers till after the First World War, and we got the nitrates and phosphates and potassium from the gunpowder and explosives left over after the war. The whole reason why we started using fertilizers was merely just because we had a surplus of stuff that would explode left over from the First World War. With fertilizers, one challenge they do have is they contribute to eutrophication, which you'll talk about later on in your classes, unless you've already talked about it. That's a picture of eutrophication in Florida along the Tampa Bay. And that happened because a fertilizer factory had a wastewater lagoon that developed a leak and dumped all of these phosphates and nitrates into the estuary of Tampa Bay. Now, another thing with agriculture is understanding why things taste differently. And here's an example of the difference between our old way of growing food and the modern green revolution. The tomato on the left is a grocery store tomato, and it looks like a tomato. It's grown with NPK. The tomatoes on the right that are like kind of lumpier looking, I think those are actually Saldaki tomatoes. It's an heirloom variety. Those are the bougie ones that rich people buy at like Whole Foods and Trader Joe's, or if you're lucky, just go to a farmer's market or maybe grow your own. If I gave you a slice of each of those tomatoes, you would find the one on the right tastes better. The crazy thing is you can't usually get children, like little kids, to eat a grocery store tomato. But if there's tomatoes growing in someone's garden, they will be eating them right off the plant because they have more flavor. So this is a factory farm tomato, and it's a watery crouton of despair if you eat it. I do eat them because often it's the only one I can find at the store. If you ever have a chance to grow your own tomatoes, I recommend it because those other tomatoes, which we'll just call the farmer's market tomatoes, those are grown using crop rotation and compost and often even other nutrient additives like green manure. Those actually taste like tomatoes, and the flavor of tomatoes comes from this thing called lycopene. Now, if any of you have Italian descent, you will know from your grandmothers and mothers that, like the tomatoes, or even your grandfathers and fathers, tomatoes are supposed to be cooked in olive oil. Turns out olive oil is ideal for releasing the lycopene to give the tomato more flavor. So that's why it gives a richer sauce flavor if you cook the tomatoes in olive oil rather than vegetable oil. Now, lycopene is what makes a tomato taste like a tomato, and these have more lycopene than that. Going with that, lycopene has all of these additional health benefits. And the reason why is the traditional way of growing tomatoes in a garden or on a small farm with actual soil and not using nitrates, phosphates, and potassium is because NPK is an oversimplification of what plants need to grow. There's a little phrase I learned in college, and it's Chopkin's Cafe is mighty good. And that's just an acronym to remind you of all of the elements that plants need to grow. And it's carbon, hydrogen, oxygen, phosphorus, potassium, iodine, nitrogen, sulfur, calcium, iron, magnesium. Now, in the case of lycopene in tomatoes, lycopene requires sulfur and calcium in the soil, which NPK doesn't generate. And that's why store-bought tomatoes often have less flavor than like the crazy hippie person at the farmer's market that's got some really good tomatoes. So that's a little bit. And by the way, with that, that gets into a nutritional perspective as well. It's also good to know about soils and landfills because that's where we put our landfills. In the old days, we used to line our landfills with clay because it's impermeable. Because it has no porosity, no permeability. We now actually, modern landfills are lined with sand, clay, and plastic, and they have all these other things, as well as monitoring wells. Um, the reason why I want to talk about clay again and landfills is because of this case study. It's called Love Canal in upstate New York. If you've never heard of it, it's time you hear about it. And I get to say some really fun words. So, Love Canal was a subdivision in Niagara Falls, New York. Love Canal was built around the 1950s, and there was a land use map of it from before the 1950s. The red area is called the containment area, which that became a subdivision. And when I say a containment area, it was a hazardous waste dump. The history of Love Canal is crazy. So this guy named Henry Love, I think was his name. Yes, that was his name. He was kind of like a Groot criminal mastermind of some sort. He decided he was going to build a trench and bypass part of the water from the Niagara River and pull water away from Niagara Falls and run it through a trench on his property to make electricity to sell back to the state of New York. And, they didn't stop him, so he started digging this trench. He ran out of money after the trench was about a half mile long. You'll see it in this picture. Filled with water naturally because it was below the water table. He never had his dream of bypassing and pulling water away from the Niagara Falls. People actually used it as a swimming area for a little while, and yes, the name of the company was Hooker Chemical. Hooker Chemical bought it at public auction because it was abandoned. And they got a giant hole in the ground, so they're a chemical plant company, Hooker Chemical, and they decide to pump it full of all of their old chemicals. Now, there's a weird thing in US law. We didn't require tracking of hazardous waste before 1976. It's this law called the Resource Conservation Recovery Act. So this is long before 1976, and they just threw everything in there. And when I say they threw everything in there, like trucks would pull up, dump things in, they'd throw barrels in, and they just made like a giant hot, soupy mess disaster of unknown chemicals. One of the companies that turns out, or one of the organizations that was using this was the Manhattan Project, which means besides various sketchy chemicals getting thrown in here, radioactive waste from the Manhattan Project also went into here. This is how Love Canal looked in the 1980s. That whole area where you see like the winding streets and the apartments and the schools, that is on top of the hazardous waste dump. None of the homeowners knew of this, and they all started getting sick. Here's an infrared photo from the 80s where you see the little white patches in the grass. That was actually caused by ooze coming out of the ground that was killing the grass. So that area, if you played in those areas, the dust would give you chemical burns. So here's other pictures of it. So the whole area ended up having several hundred homes on it. And what happened was in the 1950s, the city of Niagara Falls bought the land for $1 from Hooker Chemical. The reason why they did this, and they got this huge swath of land, is Niagara Falls was a growing area. And sometimes people will do these things. They're like, wow, we'll buy all this land. They're being so generous to us. They must be doing it for a tax write-off, selling us this land for only $1. And then as they sold and divided up the land, they used the money to build several schools. So there's 2 elementary schools and a high school on top of a hazardous waste dump, as well as several hundred homes, and no one had been told their homes were on hazardous waste dumps. Now, you've probably heard adults say that annoying thing, if something is too good to be true, it probably is. The crazy thing is these were like smart adults who bought a chemical landfill for $1 from Hooker Chemical. By Hooker Chemical selling them the stuff for $1, that meant the city of Niagara Falls was not responsible for the landfill. Like they just they ditched it with the city and they're like, okay, it's your responsibility now. People started getting sick there in the 70s. And it spread rapidly. Like there were higher rates of cancer, birth defects, mortality, miscarriages. One mother became one of the first activists. Her name is Lois Gibbs, and you can see interviews of her on YouTube. She only had a high school education, no background in science, and her son developed epilepsy, and that was what got her interested in what was going on. She lived on the hazardous waste dump, and she didn't know it was a hazardous waste dump. Now, with epilepsy, there's a few things that can cause epilepsy, including brain injury, genetic history, or heavy drug and alcohol use. Her son did not meet any of those criteria for genetic history or anything. It just developed. And researching what was going on, she started talking to neighbors and found out everybody else had weird health problems. And she and a group of neighbors sleuthed out that their whole neighborhood was on top of this hazardous waste dump called Love Canal, and no one told them. And the weird thing was the neighborhood was called Love Canal. So that's what goes from it. What happened in Love Canal was when the city bought the land, what Hooker Chemical did was they covered the top of it with a thick pack of clay. And the Love Canal area full of the hazardous waste was also lined with clay before they filled it with, the chemical soup of badness. When clay dries, it cracks. And that's what ultimately happened is the clay dried out and cracked and started leaking the stuff into the groundwater. And it didn't just affect the homes on top, but it affected homes in the surrounding area through lateral flow of the groundwater. So in the end, with this Love Canal hot mess, it sucked because imagine you're living on a hazardous waste dump. What can you do? And so the weird thing was the homeowners found out, they went to the city, and the city's like, oh, that's Hooker Chemical's fault. And Hooker Chemical's like, no, it's your fault because you bought the land from us for $1. So they were acting like a bunch of brats. All of them. And meanwhile, people are getting sick. You can't sell your house and move because no one's going to buy your house. In the 70s and 80s, this was in the national news every night talking about what happened at Love Canal. And, hundreds of families were impacted. And the other thing is your house lost all value because it's on a hazardous waste dump. It sucked for everyone involved. Ultimately, the three groups that were found to be partially responsible were Hooker Chemical, which made it more confusing as Hooker Chemical officially stopped existing. They dissolved their corporation. However, then they took their assets and formed a new corporation called Occidental Petroleum. Occidental Petroleum, by the way, still exists. And believe it or not, they actually own the oil fields for the Gulf Horizon oil spill. They bought that after that. So if you ever see an Occidental Petroleum sign in your neighborhood, you might want to do some researching. It's probably a good time to leave. I think they're the harbinger of doom. Now, these three entities were all considered responsible because it turns out the biggest user of Love Canal was the U.S. Defense Department. But in the 1970s and 80s, nothing was getting done for these homeowners who were stuck there getting sick. And they couldn't even, and they didn't have money to buy a different house, so they have to live there and get sick. What they ended up, and by the way, one of the other activists was this woman, PJ Brown. What these activists did was hilarious and completely illegal. At one point, they were complaining. No one was doing anything. It was now in the national news. No one was helping them. And the EPA came and actually had a one-on-one to talk to a few people in this community group. And they kidnapped the EPA officials. And they held them hostage until the EPA finally coughed up the money to buy all of their properties and help relocate them to new homes. And by the way, that created the governmental policy called Superfund. And it was started by a group of angry people who literally kidnapped two EPA officials and held them hostage. By the way, the EPA officials dropped all charges and said they were very nice and peaceful as they kidnapped them. They fed them, let them use the bathroom, and made sure they were comfortable, and were pretty much apologetic, saying, we're sorry that we had to kidnap you, but it's the only way to get out of here. And in the end, the entire community moved, was relocated. Initially, it was just 200 homes within 2 blocks. They finally did relocate all homes in the Love Canal area, but it took a long time. Hooker Chemical, which became Occidental Petroleum, was found negligent, and they had to pay $129 million in 1995, which was 20 years after people started getting sick. And the thing is, they couldn't scoop out the toxic stuff in Love Canal because it has to go somewhere. So they started containing it with on-site treatment. They've identified over 200 chemicals, including dioxin and chlorinated benzene, that are endocrine disruptors, neurotoxins, and can increase your risk of cancer. By the way, they redeveloped Love Canal, and you can now buy houses on Love Canal. They're intentionally targeting people born after 1990 with the properties. This time on the deeds, there is a disclaimer that says no one will be responsible if you get sick. So now that we're done with that sadness, by the way, we're going to go on to some happy things, because part of it is talking about ways to grow our food without screwing over future generations. And there are some really good solutions. One is polyculture, another is swidding. The one key is both require going back to smaller farming. So this, by the way, this guy with the chicken is right here as well. His name is Joel Salatin from Polyface Farms. You can see little YouTube videos about him. The guy is hilariously insane in a good way, sometimes. His background was he inherited this cruddy farm from his grandfather when he passed away, and he decided to get back into farming. It had been overfarmed. There was so much erosion, bare rocks were sticking out of the dirt, and it sucked. And in his interviews, he started this Polyface Farms probably about 20 years ago. And in one of his quotes that was amazing, he's like, "It started with the chickens." His chickens got out of the chicken coop, found the compost pile, and were digging away in the compost, pooping in the compost, and ended up that the chicken poop made better soil than he'd ever seen before because it's hotter and higher in nitrogen, and it sped up the decomposition. So rather than having a traditional chicken coop, he redesigned it by putting the chicken coop on wheels and called it the Eggmobile, and would just wheel it all over the farm. And wherever the chickens were on the farm, it started improving the soil quality. Plus, the chickens were eating insects, and worms in the soil, which gave them better eggs than just feeding the chickens corn because they had a richer egg yolk, and that meant that the eggs actually had higher omega-3 oils and actually taste better. And then he added cows into rotation. And then he even added pigs into the rotation at the tail end. One thing he noticed was in the dairy barn, he started moving the dairy barn every few months rather than swapping out all the manure. He did find out that the cow manure doesn't always decompose well. So he started throwing feed corn into the cow manure as the cows were pooping. And after he got rid of the cows or moved the cows to a different area, he would set up a pig pen, and then the pigs would dig through the cow manure looking for the corn, and somehow that turned over everything. And now he's added rabbits as well to his rotation. His farm produces more protein per acre than any other farm, than any traditional large-scale farm. He's also adding 1 inch of topsoil now every year to his farm, and he's making a fortune. And he now actually trains people on how to do this polyculture, and people are like, "How do you do this? Like, why is it so profitable?" And he's like, "It's profitable because it's small." He's like, "You can do this as well." So this is one solution in the U.S. from this guy, Joel Salatin, and it's taking off. If you've seen The Biggest Little Farm in your class, that is based. They actually got a lot of their practices by reading up on what Joel Salatin did in his farm. Now in Central America, there's other examples of this, and this is called permaculture. And permaculture is just ways of reducing waste by composting, using perennial crops, doing what we call closed loop agriculture. Doing these things can help reinvigorate your soil, decrease erosion. It also decreases pest damage, and it rebuilds your soils. And remember how I mentioned that in tropical rainforests, we don't have topsoil here. You've probably heard that slash and burn is wrong and bad, and it depends on the slash and burn. Here are some pictures of a swidden field. This is where traditional populations in Central and South America and other tropical rainforests in the world, how they produced food. They would cut down a patch of forest, not like 1,000 acres, but maybe the size of a tennis court or a basketball court. They cut down the trees and they burn it. And that's important because they have to burn this stuff to build up some soil and organic content because there's no organic content. They would plant crops that they could harvest that year right away. They would plant what are called perennial crops and fruit trees that would grow in. And basically they could, and you'll see these in these pictures where this is a new swidden field. This was a 20-year-old one, and you can see the forest is already growing back. And this was one in mid-use. In doing this, they trick the forest into regrowing, and they do a huge amount of food production sustainably. So now we refer to the sustainable slash and burn as SWIDDing. When the conquistadors came through the Americas, they thought everybody was living in harmony with nature. What they didn't realize was they were walking through SWIDDing fields, unaware that this was actually a re-engineering of the forest for food production. And by the way, the other reason why they thought the indigenous populations of the Americas were living in harmony with nature was actually because a lot of them had died from infectious disease before the conquistadors even stepped into their territory. But now the key thing for all these solutions is, when someone asked Joel Salatin, like, where did you come up with this crazy new technology? And he responded with, this is not new technology. This is how my grandparents farmed traditionally. And it's going back to some of the more traditional ways, but also making farms smaller. So that has completed your crash course in soils. There's more to know about soils. If you want to read some good books on it, there's a lot of good books by Michael Pollan about soil formation. Yeah, but that's great. Thank you for your time.